Today we're going to look at the cake problem. So what's the cake problem? Well, let's assume that we have a cake of size x. Okay, and you have to decide whether we want to eat the cake now or wait one period and eat the cake tomorrow. So eating the cake gives you some utility, okay, which is increasing in the size. So let's say this is u of x. But there's some twist in the sense that either it's possible that you don't really feel like eating a cake today, or maybe you're very much into eating the cake today. And we will model this by using a preference shock. Okay, so we have a variable z. So the utility of eating the cake is z times u of x. Okay, and you assume that z is strictly positive. Okay, so if you don't like eating the cake, then we have that z is equal to z, let's say L for low, right? We have a low preference for cake today, or z can be equal to z of h. And you assume, of course, that z of h is bigger than z of L. Okay, so eating the cake when you like eating today is z of h times u of x. If you don't like eating the cake today, then we have z of L of u of x. And you assume that taste may change over time, and this change over time is a stochastic process. So in the sense that the probability that z is equal to z of L today, given that it was zl yesterday, we will set this equal to some value pl. Okay, this is an L which is between 0 and 1. And the probability that your taste is equal to z of h today, given that it was z of h yesterday. Okay, so this should also be yesterday. We will set this equal to p of h. Is also between 0 and 1. Okay, so we can put this in a matrix. So here we have z today or at some particular time, and here we can z tomorrow. Okay, z today can be either zl or zh, and then z tomorrow can also be zl or zh. Okay, and if z is equal to zl today, then it will be equal to zl tomorrow with probability pl, and then of course it will be equal to zh with probability 1 minus pl. Okay, z today, if it's equal to zh, then it's equal to zh tomorrow with probability ph, right? This is this probability, and then of course it will be equal to probability 1 minus ph with zl tomorrow. Okay, so this is, you can call this a transition matrix, or the transition probability matrix for the taste. So the question is the following: when is it optimal to eat the cake? And there's a particular twist to the problem. You will assume that waiting for 1 day reduces the size of the cake by a fraction 1 minus delta. Okay, so there's a delta strictly between 0 and 1. So if you have this is cake of size x today, then tomorrow, if you wait one period, then the size will only be delta x. So delta can be interpreted as where does it come from? Well, it might be that a part of the cake turns bad, or the cake is not as nice anymore if you wait it for a longer period of time, right? The cake perishes. You cannot store it forever. So every time a fraction 1 minus delta goes away. Okay, so you would like to model this as a stochastic dynamic optimization problem. So what do we do well, first we have to decide on the state of the problem. Okay, so what's the state? The state is here going to depend on x, right? Deciding whether to x gives you the size of the cake, and it reduces by a fraction 1 minus delta every time period. So here the state is going to be x, which is the size of the cake, but we're going to also include into the state the value of z, okay, the taste shock, either low or high. Okay, so it will depend on two parameters, x, the size of the cake, and z, the taste. And then what are we going to do? Well, we're going to decide to eat a cake or wait one period and maybe eat the cake later on. Okay, so let's try to write down the Bellman equation. Okay, so we have u of x and then z, and we would like to write this as a maximization problem of eating or not eating, of the value when eating and the value when not eating, and then taking the maximum. Okay, so let me write it down. So if the state would be ZL, well, then if I eat the cake, I receive this amount of utility, okay, ZLU of x. And if I wait a period, well, assume that I have a discount range beta, which is between 0 and 1. And then it depends on what's going to be the taste shock tomorrow. Okay, so if the state is today ZL, then with probability PL, I will have a taste ZL tomorrow. Okay, that's here. And then I will face the same problem again. So let me call this V. V is the value of the Bellman equation, right? In order not to mix up with the U here. I have V. What's the size of the cake tomorrow? Well, it will be delta times x, because the cake reduces in size. And then I will have the taste ZL. And then with probability 1 minus PL, tomorrow I will have a size delta x, and I will have a taste ZH tomorrow. Okay, so this is the Bellman equation. This is the payoff when I decide to eat. This is the payoff, the expected payoff when I wait, and I'm going to choose the maximum of these two. If this is bigger, then I'm going to eat the cake. If this is bigger, then I'm going to wait. And we can derive a similar equation in case my taste is ZH. Then if I eat, I will receive ZH times U of x. If I wait, I discount with the rate beta, and then I will have probability 1 minus PH. I will move to state ZL, so I will have payoff V delta x ZL, and then with probability PH, I will have value of delta x and ZH. Okay, so this is my Bellman equation that I would like to solve. So for basically I have an equation for state ZL and I have an equation for state ZH. So in general I have an equation depending on the state X and the taste shock Z. So the question is now, can we say something about the solution to this maximization problem? Okay, so here I've written down again the two Bellman equations of our problem. So the first thing that we're going to show is that, well, it is always optimal to eat, right, to eat a cake when Z is equal to ZH. Okay, so if I'm at a high state, taste shock, I will also always choose this one here. I will always eat the cake. If I'm at a low taste shock, maybe yes, maybe no, but if I'm at a high taste shock, then it will always be optimal to eat the cake. So how are we going to do this? Well, we're going to show that Vx ZH is equal to ZH U of x. right? And we're going to show this for every x. So if v x z h is equal to this here, right, which is what's standing here, then because it's equal to the maximum, of course this will be greater or equal to this one, so we're going to eat when the state is zh. Okay, and in addition, basically we're going to prove something more stronger. We're also going to prove that v x zl is less or equal to v x zh, right? We're going to prove the two things together, and you will see in a minute why we do so. So the second one says that the value of being in the low state is always lower than the value of being in the high state, which seems natural. Okay, so how are we going to show this? Well, we're going to use the Bellman operator, right? So remember, the Bellman operator is just the operator t that maps a function v to this function here, t of v. So we're going to define a set d of functions v, which are here now continuous functions bounded in some norm, but you can show, basically it's quite easy to show that this will always be bounded. Okay, so if the size of the cake x is bounded, which we assume that we start with some size x that's an upper bound of the cake. Okay, so we look at all continuous functions v that satisfy the following two conditions, namely that v x zh is equal to zh u of x, and v x zl is less or equal to v x zh. Okay, we look at all the functions that satisfy these two conditions, and then we're going to show that for every v in D, t of v is also in D, right? So the operator maps from D to D, and because D is a closed set, right, this follows from the fact that here we have equalities, right? So a sequence of functions that satisfy these two conditions, the limit, if it exists, will also satisfy these two conditions. Okay, so this is a closed set. So because this is a closed set, then we know that if this holds, if t of v is in D for every v in D, then we know that the fixed point v star will be also in D, and then if it's in D, right, because it satisfies this condition, it will be optimal to eat the cake when the state is high. Okay, so take function v in D, we need to show this, and we need to show this. So in principle, if you want to show this, then you need to show that tv of x zh is equal to zh u of x, right? That's the first thing that we need to show. And the second thing we need to show is that tvx zl is less or equal to tvx of zh. And because if we first show this and then this will, the second one will be equal to zh u of x, right? Because we can use this inequality here to substitute here. Okay, so let's first show one. So we have tv x zh, and let's just put the definition here. So we know that this is equal to the maximum of two things, zh u of x, and then beta 1 minus ph of v dx zl plus ph v dx zh. Okay, so first thing, we assume that v is in D. So for all x, vx zl is lower than vx zh. So this holds for all x. Okay, so in particular it holds for delta x. So we know that v delta x zl is lower or equal to v delta x zh. Okay, so the maximum here will be less or equal to the maximum of zh ux, and then beta, if you let this less or equal to this, then this will be equal to this. So here we have v delta x zh. And now we're going to use this condition here, but for x equal to delta x, right? So we know that this is equal to u delta x zh. So this is less or equal to the maximum of zh u of x, and then beta zhu delta x. Delta is smaller than 1 and u is increasing in x, right? So I have that this is bigger than this one, and the beta is smaller than 1. So I know that the maximum of these two will be equal to zh u of x. Okay. So tv x zh is equal to the maximum of these two. So in particular, it's greater or equal to the first one. Okay. So zh u of x is less or equal to tv x zh, and then by this derivation I know that it's also less or equal to zh ux. So these two inequalities here are in fact equalities. Okay, and this proves condition 1. So for condition 2 I need to show that tv x zl is less or equal to zh ux. So let me do this here. So I'm going to start with tv x zl, and this is equal to the maximum by definition of zl ux and beta plv delta x zl plus 1 minus probability of low of v delta x zh. Okay, and we can do more or less the same derivation here. So this is less or equal to v of delta x zh, right? By this assumption here, it holds for every x, so also for delta x. So this is less or equal to the maximum of zl u of x, and then beta, these two, this is common, right? So this is v delta x zh, and you know that this is less or equal to, or this is equal to max zl u of x, because v x zh for every x is equal to zh u of x. So the second argument will be equal to beta zh u of delta x. Okay, so the first one here, zl is lower than zh, so the first one is lower or equal to zh u of x. For the second one, u is increasing in x and beta is smaller than 1, so this is also lower or equal to zh u of x. Okay, and the maximum of these two things is equal to zh u of x. So I know that tv x zl is lower or equal to zh u of x, which is what we wanted to show in step 2. So this proves the result. In other words, when the state is high, I'm always going to eat the cake. So this result already simplifies my problem considerably, because I can simply put vx zh equal to zh u of x, right? I know the solution to the problem when the state is high, and then vx zl will be equal to the maximum of zl u of x, and then beta plv delta x zl plus 1 minus pl. And when the state is going to be high, well, I already know my v function, so this is going to be zhu delta x. Okay, so basically I've eliminated this function here, so what I'm left with is only this Bellman equation that I need to solve, right? So I already solved half of the problem because I know what to do in state ZH. So here I only have a Bellman equation in ZL, right? So the other value function disappears. And now the question is, when in the state as ZL, when am I going to eat the cake and when am I going to eat the cake? Okay, and we're going to use cutoff decision rule, or we're going to look when this kind of cutoff decision rule is valid, right? So a cutoff is a value x star such that when the cake is bigger than x, then basically we're going to wait. And if the size of the cake is smaller than x, then we're going to eat. Okay, so basically what this means is that, for example, we start here with the size of cake x. If the state is ZL, then we're going to wait. Okay, if it changes to ZH, then we're immediately going to eat, right? But it's also possible that it stays at state ZL. So we're going to wait, the size of the cake decreases to delta x. We're going to wait again, wait again, wait again, as long as the state is ZL, right? As soon as it goes to ZH, we're going to eat it. Until after some point, if we arrive below x star, then we're going to eat the cake, right? So this is basically how it goes. Decision problem is, if the state is ZL, then as long as I'm above x star, I'm going to wait. As soon as I'm below x star, then I'm going to eat the cake. Okay. So first thing that we can try to answer is, what's x star? Well, we know that at x star, below x star I'm eating, above x star I'm waiting, so at x star I should be indifferent between the two. Okay, so if I'm indifferent between the two, then the first argument here should be equal to the second argument here. Okay, so let me write this down. So we have that ZL at x star should be equal to beta times PL V delta x star ZL plus 1 minus PL ZH U of delta x star. Okay, so this equality should hold at x star. And if I use this rule, right, so here delta x star is lower than x star, right, because delta is smaller than 1. So here I face the decision whether to eat or not, given that the size of the cake is smaller than x star. But if I use this rule, then I know that I'm going to eat the cake. Okay, so here eating is going to be optimal according to my conjecture. So here V delta x star ZL is going to be equal to ZL U of delta x star. Okay, because I know that I'm going to eat, so it's going to be equal to the first argument here. So this simplifies to the following. It's beta, and then we have PL ZL plus 1 minus PL ZH, and this times U of delta x star. Okay, so I can rewrite this as U of delta x star divided by U of x is equal to ZL divided by beta PL ZL plus 1 minus PL ZH. Okay, so this gives me the utility of the cake of size delta x divided by the utility of cake of size x. So normally this will be smaller than 1. Okay, and this gives me threshold. So basically this is the return that I get when I decide to eat, and this will be somehow the return that I get from waiting. Okay, and at the part where I'm indifferent, this ratio should be equal to this ratio. Okay, so if I would have an x such that U of d delta x divided by U of x is bigger than ZL divided by this fraction PL ZL plus 1 minus PL ZH, then basically the return of the cost of waiting is lower than the benefit of eating. Okay, so in this case, what you would expect is that because this inequality doesn't hold, right? Because here the return of waiting, or the cost of waiting, is lower than here. You would expect the person to wait. Okay, so in particular, we would like this to correspond to this area. So you would assume that for all x bigger than x star, this inequality holds here. On the other hand, if u of delta x, u of x is below ZL divided by b, PL ZL plus 1 minus PL ZH, then it will probably be optimal to eat the cake. So we're going to assume that this holds for all x smaller than x star. Okay, so this is a rule that we're going to impose. So observe that it's not always the case that for any utility function u, I can find an x star such that if x is bigger than x star, then this is satisfied, and if x is smaller than x star, this is satisfied, right? So this is an assumption that we're going to make on the utility function. Okay, but we will show that if the utility function u satisfies this property, okay, then this will be the optimal decision rule. So to summarize, we're going to prove the following theorem. If it happens that the utility function is such that there exists an x star such that if x is bigger than x star, then this inequality is satisfied. And if x is lower or equal to x star, then this weak inequality is satisfied. Well, I can change this with the weak inequality and this with the strict one, right? It's almost 1 to 1. Well, then we will show that if indeed x is bigger than x star, it will be optimal to wait, and if x is smaller than x star, then it will be optimal to eat. Okay, so this is the theorem that we're going to prove. Under these conditions, these two conditions, this will be the optimal policy. Right, so let's first prove this here, and we're going to use the same strategy as we did before. So we're going to consider a set D of functions v such that if x is smaller or equal to x star, then it will be optimal to eat. So we're going to require that v of, for all x, v of x, for all x smaller than x star, v of x ZL is equal to ZL u of x. Okay, because I know that if this here holds, then it will indeed be optimal to eat. Okay, so what I need to show is I need to show that for all v in D, T of v is also in D. Okay, so in particular, TV of x ZL is equal to ZL u of x. This is what I need to show. So let's do this. I have TV x ZL. This is equal to the maximum of two things. Well, ZL u of x, and then beta PL u no, not u, but v delta x ZL plus 1 minus PL ZH u delta x. Okay, so that's the correct one. So this is for x smaller than x, right? So I need to show that for all x smaller than equal to x star, this inequality here holds. Well, if x is smaller or equal to x star, well, then I know that delta x is also smaller or equal to x star, right? Because delta is smaller than 1. So because v is in D, it satisfies this condition for all x smaller than x star. So here I know that this is equal to ZL u of delta x. Okay, because delta x is smaller or equal to x star. So I have that this is equal to the maximum of ZL u of x, and then beta, I can pull this out, the u of delta x, PLZL plus 1 minus PL ZH of u of delta x. Okay. And now, because x is smaller than x star, by assumption, this here, u of delta x times this, right, which is equal to this part here. If I bring this to the other side and bring this to the other side, I know that this will be lower or equal to ZL times ux. So this is less or equal to the maximum of this here, and then the second part is lower or equal to ZL u of x. So this is equal to ZL u of x. Okay, so this here is equal to the maximum of these two things. So the first one, ZL u of x, is less or equal to the, of course, the first part is lower or equal to the maximum of these two things, which is equal to this one. So this is lower than TV of x ZL. And here, this derivation has shown that this is lower or equal to ZL u of x. So here, TV is sandwiched between two terms that are equal. So here we have equalities. Okay, and this shows the first part of the theorem. So for the second part of the theorem, we're going to use other sets. Okay, so let me use a set D. It's going to be the set of functions V, such that for all x smaller or equal to x star, I'm going to keep this here. Vx ZL is equal to ZL u of x, and for all x greater or equal to x star, well, I'm going to assume that it's optimal to eat, right? So the second part of the maximization problem, where did I have my maximization problem? If I have written it down here somewhere. Well, you know the maximization problem I'm talking about, this one here, right? So the second part is going to be bigger than the first part. I'm going to wait. So I'm going to assume that ZL u of x is lower or equal to beta times PL V delta x ZL plus 1 minus PL ZHU delta x. Okay, so this is the set. This is my closed set, right? This is closed because I use weak inequalities, and then I'm going to use a variation on this. So for all x smaller or equal to xv, x ZL is equal to ZL u of x. If x is smaller than x star, then I'm going to eat. And for all x bigger than x star, here I will use this, but with a strict inequality. ZL u of x is smaller than beta PLV delta x ZL plus 1 minus PL ZHU of delta x. So if x is bigger than x star, then it will be strictly optimal to wait. Okay. So what I'm going to do, I'm going to show that for all v and d, T of v is in the tilde. Okay, and this will show that the fixed point is in the tilde, so it will satisfy the policy rule. Getting mixed up. It will satisfy this policy rule. Okay. So that's what I'm going to do. So first of all, notice that as D is a subset of the D I first used in the first part of the theorem, it will map to a set that contains this one, right? So from part 1, I already know that for all x smaller than x star Vx ZL is equal to ZL U of X. I already have proven this in the first part of the theorem, so I only need to show this here. I need to show that for all x bigger than x star, ZL U of X is smaller than beta PL, and now becomes here TV delta X ZL plus 1 minus PL ZHU of delta X. Okay, this is what I need to show. So let's have a look at this term here. So we have TV delta X ZL. We know that this is equal to the maximum of ZL. Now here I have delta X, right? So the state is delta X, so this is U delta X. And the second one is beta PL V delta times delta X, right? So this is delta squared X, ZL plus 1 minus PL, and then I have U delta squared X. Okay, so there are two cases. Either delta squared X is smaller than X star, or it's smaller or equal to X star, or it's bigger than X star. Okay, so if it's smaller or equal to X star, then because V is in the set here, right, I have V delta squared X ZL is equal to ZL U of delta squared X. Okay, so in this case here, I have V of delta squared X ZL is equal to ZL U of delta squared X. Okay, in the second case, I can use this thing here, but now with delta squared and delta squared here, right? So this entire thing here, entire second part, beta PLV delta squared X ZL plus 1 minus PL U delta squared X. Now I have to look, will be greater or equal to ZL. This was Ux, but now it is ZL U delta X. Okay, so in case 1, I have that this is greater or equal to the maximum of ZL U delta X, and if I plug this in here, take it outside our brackets, I have B PL ZL plus 1 minus PL ZH U delta squared X. Now, because delta squared X is lower than X star, it comes to this condition here. So instead of X, I have now delta X. So this becomes U delta squared X times this thing here, which is this part here. This will be lower or equal to U of delta X now times ZL. Okay, so the second part here is less or equal to ZL times U of delta X. Okay, so here I have the maximum of ZL U of delta X and then something else that's lower or equal to this first part. Okay, so if I take the maximum of these two things, I will have that this is equal to ZL U of delta X. Okay, so far we have shown that here this part is greater or equal to ZL times U of delta X. So now let's return to what we want to show, which is this one here. So let's start with the right hand side. You have beta PL TV delta X ZL plus 1 minus PL ZHU of delta X. I know that the first part by this derivation is greater or equal to ZLU delta X. So I know that this is greater or equal to beta PL ZLU of delta X plus 1 minus PL ZH of U delta X. this is equal to beta PLZL plus 1 minus PLZH U of delta x. And then by assumption, because x is, what was it? X is bigger than x star. So I have to look here. So this thing times this thing is strictly bigger than U of x times ZL. So I know that this is strictly bigger than ZL times U of x. Okay, which is here what I needed to show. Okay, so indeed we have shown that for x smaller than x star, it's optimal to eat. For x bigger than x star, it's optimal to wait. Thanks for watching.